Hi, this is Dr. Tortories. I am creating a key for the worksheet that I had my students work on in class on Thursday, January 30th, when I had a substitute. Some of the other teachers also use this worksheet, so you might find this key helpful. And if your teacher didn't assign you this worksheet, the problems are written here, and then I'll be working through them, and so it might be great additional practice for anyone. So here we go. Number one is actually a problem that doesn't require as much work as you might think. It has a lot of information, but basically it's telling you that there's a change in kinetic energy as the ball falls of 500 joules, and then it asks you how much work gravity would have done on the ball between points A and B. And because of the work is equal to the change in kinetic energy theorem, it means that they gave us the answer right here. The work is going to be equal to the 500 joules. And the work would be positive because the ball is going down, so our displacement is down, and our force, because of gravity, is down as well. Moving on to number two. Okay. We always want to go through and read the question over first, get an idea of what's happening. It's clear there's a force and a distance, and energy is being transferred to the ball. So the fact that there's force and distance would say something about work and energy transfer. When work is done on an object, it causes a displacement, which means it's moving, which means it has a velocity, which means that we're going to be dealing with the work kinetic energy theorem. And what you also want to remember is that work is, of course, equal to that force times displacement. So that means that the change in kinetic energy is equal to force times displacement because of transitive properties. If work equals change in kinetic energy and work equals force times displacement, then kinetic energy equals force times displacement. So we have a force of 6 newtons. We have a displacement of 0.6 meters. And that's it. We're asked for energy. And so when we plug in our information, we have 6 newtons times 0.6 meters, which will give us 3.6 joules of work done on the ball. And the work is transferred into kinetic energy. Okay. All right. Moving on to number 3. Here what we're keeping in mind is that when work is negative, the direction of force and displacement are opposite. So one's up and the other's down. When work is positive, they're in the same direction, whichever way that might be. Okay. I guess we can show going either way. Okay, so then also you want to keep in mind that if there is no displacement, then there's no work. Okay, so we have a heavy backpack at rest. There's no displacement, so there's none for work. Brakes applied to a moving car, causing it to slow down. The brakes are doing work in the opposite direction of the car's motion to cause it to slow down, so this is negative work. A ball thrown up into the air, it's slowed down by gravity, so the ball is displacing up while the ball is traveling, while the force is acting downwards on it, so that is, once again, negative work. The slowing down is a good key that you've got negative work happening if you're being asked about work. Okay, here we have wardrobe that doesn't move, so there's no work. And here we have a ball gaining speed as it falls towards the ground due to gravity, so since displacement or force in the same direction, we have positive work. Okay, and for number 4, we have a go-kart with no engine along a flat frictionless surface with a speed of 4 meters per second. The mass of the go-kart is given. The go-kart reaches a downhill slope, which is going to, of course, make it go faster. It's on a frictionless surface, and it's going down, so things get faster as they go downhill. And afterwards, this go-kart speed is 5 meters per second, and we want to find the work done on the go-kart by gravity. Whenever you have a change in velocity, that's going to indicate that you have a change in kinetic energy, and we're being asked, of course, about the work done by gravity. So we want to go ahead and list our variables that are related to work and change in kinetic energy. So we have an initial velocity that's equal to 4 meters per second. We have a final velocity that's equal to 5 meters per second. We have a mass that's 80 kilograms. Okay, and our work is going to be equal to our change in kinetic energy, which is going to be equal to our Kf minus our Ki. Okay, and then we want to expand both of these into, so our work is going to equal 1/2 mvf squared minus 1/2 mvi squared. Okay, a little shortcut, we can actually factor out the 1/2 m because it's common to both parts of this problem, and so we can change this to work is equal to 1/2 m times vf squared minus vi squared. You don't have to do that, it's going to come out to the same answer either way, but that can, just save you a little bit of calculation. So plugging in our numbers, we have 1/2 of 80 kilograms times 5 squared minus 16 squared. So that comes out to be 40 times 9, because 5 squared is 25, and and I wrote 16. I went ahead and wrote the answer, sorry. 4 squared is where we get our 16 from. So 25 minus 16 is 9. Sorry about that. My brain sometimes doesn't keep up with what my hands are doing. Okay, so 40 times 9 is going to give us 360 joules of work done by gravity on the go-kart. Okay, this is actually a very similar problem. We have a mass given to us. We have an initial velocity given to us. The final velocity of 0 is implied. And then we're asked for the work done by the brakes. Now in this problem, we still have work is equal to change in kinetic energy, which is going to be Kf minus Ki. In this particular problem, though, it's useful to note that since the final velocity is 0, right here, then Kf is going to be 0 minus the 1/2 mvi squared. So it's a little bit easier to not factor this one out and just remember that we're dealing with negative for our product. And that would make sense because the truck is coming to a stop or slowing down. So the work done by the brakes is going to be negative. So we have 1/2 times 2,000 kilograms times the initial velocity of 25 meters per second squared. And from that we get negative 625,000 joules of work done by brakes on the truck. All right, for this one, this is going to be, again, where we basically have, because work equals change in kinetic energy and also equals FD, then change in kinetic energy equals FD. That's basically what we want to look at. And we're looking for basically a final velocity here. What's our final velocity? And the things that we're given is mass of 0.2 kilograms. And we have a force applied of 10 newtons. And we have a distance of 0.25 meters. So this right here is what gave me the indication that we were going to need to use this right here in conjunction with our change in kinetic energy. So in order to find speed, because kinetic energy is the formula that has velocity in it. So what we're going to do is set up our expanded version of change in kinetic energy. Okay, and in this case, the Kf is going to equal this. The Ki is going to equal 0 because it was initially at rest. So Kf minus 0 is just going to be Kf. So I'm just going to leave this as it looks right now and set that equal to force times displacement. and our force times our displacement is 10 times 0.25 meters. Oh, so I sort of skipped a step there. So it's 1/2 of 0.2 VF squared equals 10 times 0.25. Personally, I like to completely write out the rearranged equation, so I just have to put everything in the calculator once, and then I won't get any rounding errors. So that doesn't look very much like a 1, so there we go, 10 times 0.25. Okay, so basically then what we've got is that VF squared is going to equal...
Good morning, teacher.
Okay, I have to pick up again. I had to pause the recording for a moment. All right, so rearranging that, we have VF squared is going to be equal to our 10 times 0.25 divided by 0.5, which is rewriting of 1/2 times 0.2. And then we are also going to have to take the square root of that in order to find VF. And when we put square root of 10 times 0.25 divided by 0.5 times 0.2, we get 5 meters per second as the final velocity of the puck after the force has been applied. All right, number 7. Okay, for this one, we want to list our variables. We've got our mass of 18 kilograms. And we have an initial, whoops, not a final, we have an initial velocity of 1 meter per second. We're going to have a final velocity because it's asking until it comes to a stop, so we're going to have a final velocity of 0 meters per second. And we're also given a coefficient of friction of 0.5%, which may be something that you haven't really thought about much for a while, so equals 0.5. And there's no unit for coefficient of friction, so I'm not putting one. Okay, and then it also reminds us that gravitational acceleration, or little g, is going to be 10 meters per second squared, which of course we should know anyway. All right, so looking at this, we know that we're going to need to use the fact that work is equal to FD is equal to change in kinetic energy. And we want to keep in mind that our final condition is 0, so that means that our final kinetic energy is going to be 0. So when we do 0 minus our Ki, basically that means that the change in kinetic energy is equal to negative Ki, so then we don't have to worry about putting that Kf in. And so basically then too what we have is that negative Ki is going to equal the force times the displacement. Now we do need to get this force of friction, and that's where this mu right here comes in. We've got to use that in order to find the force of friction, and as the hint says, drawing a free body diagram might help you out with that. So in order to find the force of friction, using mu, you need the normal force times mu. So our normal force is going to be equal to the gravitational force, which is equal to m times g, and so our m is 18 kilograms, our g is 10, so our normal force is 180 newtons. So 180 times our coefficient of friction of 0.5 is going to give us a force of friction that's equal to 90 newtons, because the normal force is 180 newtons, because the Fg is 180 newtons. All right, so now we have our force, and what we are trying to find is displacement. So now we have everything that we need, because for Ki, we're talking about, and I'm just going to erase this to make a little bit more room for myself. Okay, and so now what we're going to do is we're going to, I'm going to move this over here, and I'm going to say we've got negative 1/2 of our mass, I'm expanding the formula, which is 18 kilograms, times the initial velocity squared, which is 1 squared, is going to be equal to our 90 newtons times the displacement. So rearranging that, we get that displacement is equal to the negative 1/2 times 18 times 1 squared divided by 90. And that comes out to be 9 divided by 90, which comes out to be 0.1 meters of distance before it comes to a stop. Okay, moving on to number 8. Here we've got a mass given to us for our rock shot up in the air. We've got a height or displacement, same thing, really right, 13 meters. And it's telling us to use a g of 10 meters per second squared. And we're being asked about the amount of work that gravity would do. And so, of course, work is going to be equal to force times displacement. Force is going to be equal to, this is actually really a problem that comes from the very beginning of this unit before the first test. Force is equal to, in this case, we're talking about the Fg of the object, so it's going to be mg, so our work is going to equal our mg, really d or h, which of course is our potential energy formula. So when we plug in our 2 times 10 times 13 meters, we get the work done by gravity on the object as 260 joules. And that's positive because the rock is on its way back down from the highest point until it reaches the starting position, while the force is also, of course, down. Moving on to number 9. Okay, this is asking about accelerating the car to twice its initial velocity. So really, when we see this, when we see something like we've got rest to 15 and then from rest to 30, we have a twice the change in velocity. So when we look at work is equal to the change in kinetic energy, what we want to think about there is the fact that work is equal to, in a sense, if we're looking at the change in kinetic energy, and at rest is the initial condition. So with rest being the initial condition, the initial kinetic energy is going to be 0, which means really we're just looking at the change in kinetic energy is going to equal our final kinetic energy. So therefore it's just equal to 1/2 mv f squared. And so work is equal to 1/2 mv f squared. This is proportional reasoning. If we increase velocity by a factor of 2, we have to remember that that factor that we increase velocity by has to be squared because velocity is squared. And so that means that work is going to have to be 4 times as much to keep that proportional to the original equation. So it's going to be 4 times more work than was done to get it to 15 meters per second. So 4 times 112,500 joules is going to be 450,000 joules. Now you want to be careful, this is kind of like the bonus on the quiz. That isn't the final answer. That's the amount of total work needed. So this is the work total that's needed to get it to 30 meters per second, but it's asking how much additional work to this original amount right here. So we have to subtract this amount right here from this amount right here. So 450,000 minus 112,500, which gives us 337,500 joules more work. That's a R right there, not that you can tell. Okay, so that would actually be our final answer. All right, 10. We have a 50-gram parachutist. Kilogram, that'd be a tiny parachutist, who falls with a constant velocity. So our initial and our final are 6 meters per second. And then we have, and this is a little bit different than what we've seen, we have an initial height of 300 meters, and we have a final height of 500 meters. So we actually have a change in height of negative 2,500 meters. And it's asking about work, and work is equal to FD. And F in this case is equal to FG, which times D, which means that this is mg and then we can say height instead of displacement. So basically what we need to do here is just put in, and essentially too what we're looking at here, this is a change in height. Okay, so we want to put in this change in height that we have right here for our height. So it's going to be the 50 kilograms times the 10 meters per second squared of gravity times the negative 2,500 meters. And that's going to give us negative 1,250,000 joules of work done by air resistance to keep the parachutist falling with a constant velocity. If only gravity was acting on the parachutist, then the parachutist would be accelerating. But air resistance is acting opposite the direction of the parachutist's movement down, causing them to descend at a constant rate. And so that's also why our work, as it should, ends up being negative 1,250,000 joules. All right, and wrapping it up with our last problem, number 11, we have a 3,000 kilogram truck. It has an initial velocity of 25 meters per second. Fully applies the brakes until he comes to a stop. So, I'm sorry, and I just wrote that backwards. I said initial, but I wrote final. An initial velocity of 25 and a final velocity coming to a stop of 0 meters per second. And we have a displacement of 70 meters because 75 minus 5 meters before the light. It's going to give us a displacement of 70. And it's asking for the average force applied to the brakes. The fact that it's asking for average force doesn't really mean anything special. It just means that the force may not have been constant while the brakes were applied, but we can find the average strength of the force over the entire time that it was applied, as if that was what happened. Okay, so for this one, we have change in kinetic energy being equal to work being equal to FD. And again, we have a situation where because our final velocity is 0, that means our final kinetic energy is 0. So that means that the change in kinetic energy is equal to negative Ki, because it's usually Kf minus Ki. If Kf is 0, it's 0 minus Ki. So we can drop the 0 and just call it negative Ki. What you have to remember is that it isn't the velocity that you're squaring that becomes positive, therefore. It's the whole value that we make negative after we've computed everything within that value. So our change in kinetic energy is equal to negative Ki, which is therefore equal to Fd. So we have negative Ki equals Fd. So we have negative 1/2 of 3,000 kilograms times 25 meters per second squared is equal to the force which we're trying to find times the 70 meters displacement. So force is equal to 1/2, negative 1/2 of 3,000 times 25 squared divided by 70. And the force you come up with is technically negative 13,393 newtons. So that's our answer. However, that negative doesn't really matter. And in this case, it doesn't matter because we're using scalar quantities. These are all scalar quantities to find a vector quantity. And that means that the negative in this case is really meaningless because we don't know if the truck was going right and the force applied by the brakes was to the left or vice versa. It's opposite. So that means that the work is negative, the work that the brakes do is negative, but we don't know if it's because the truck was moving in the negative direction or because the force was in the negative direction. So we don't really know that this is negative. And that's it. All right, I hope that this helps you review how to work through these problems and kind of think through them. And good luck on the test. Bye.